When people think about green hydrogen, they usually picture solar farms, giant wind turbines, or futuristic electrolyzers splitting water into hydrogen and oxygen. But behind every clean molecule of hydrogen lies an overlooked story, the story of water. Hydrogen production doesn't just need water, it needs water that is nearly perfect, ultrapure, stripped of salts, metals, organics, and every trace of contamination. This is why water treatment becomes a hidden cost in hydrogen projects, one that quietly determines whether a project is viable, bankable, and sustainable. At first glance, water treatment might seem simple, like plugging in a filter before the electrolyzer. But when you zoom out across the development stages of a hydrogen project, the picture is more complex. At pre-feasibility, water treatment is just a placeholder, a quick assumption made to test economics. At feasibility, it is a finely engineered system, costed in detail, and tied directly to whether financiers will greenlight the project. This is where hydrogen's hidden cost truly emerges. Reverse osmosis, or RO, is the backbone of almost every water treatment train in hydrogen. In the pre-feasibility stage, it is treated as a given. Developers might assume a standard RO skid for municipal water or a seawater RO unit for coastal sites. They'll assign benchmark costs, maybe 40 cents per cubic meter for brackish water or $1 for seawater, and move on. The point here is not precision, it's screening. If desalination adds too much to the hydrogen cost, the project might already be in trouble. But at the feasibility stage, RO is dissected. Engineers analyze the feedwater chemistry, silica content, boron, hardness, microbial risk. Pre-treatment systems are designed with media filters, cartridge filters, and chemical dosing. Recovery rates are modeled, energy use is simulated, and energy recovery devices are integrated. Specific membranes are chosen, DuPont, Toray, or Hydronautics, and vendors provide guarantees on performance. The CapEx is quoted, the OpEx is itemized, and redundancy is built in to satisfy lenders. What was a rough assumption at pre-feasibility becomes a complex and bankable design at feasibility. Deionization, or DI, tells another story of transformation. In pre-feasibility, DI is just penciled in as a polishing step. The assumption is simple. Add 10 cents per cubic meter for resin regeneration and assume the water will hit the required conductivity. There is little concern with chemical handling or waste, but feasibility paints a very different picture. DI resins require regeneration with hydrochloric acid and sodium hydroxide. That means chemical deliveries, safety procedures, storage infrastructure, and waste disposal. Resins degrade over time, and replacements cost money. Health and safety regulations create additional compliance costs. Suddenly, the cheap polishing option looks more expensive, more dangerous, and less scalable. For a 10-megawatt pilot project, DI might be acceptable. For a 200-megawatt commercial plant, DI often becomes a liability. Electrodeionization, or EDI, often steps into that gap. At pre-feasibility, EDI is described in broad strokes, a chemical-free alternative to DI with higher CapEx but lower OpEx. Developers note the continuous regeneration process and assume modest power consumption. But details are thin. At feasibility, EDI becomes a serious contender. Stack designs are specified, electrical loads are modeled, and integration with RO permeate is fine-tuned. Because EDI requires low-conductivity water to begin with, the RO system must be optimized for consistent performance. Vendors such as Veolia or Evoqua provide technical guarantees and warranties. Engineers model long-term OpEx savings from eliminating chemical regeneration. The safety benefits are highlighted to investors who prefer solutions that reduce chemical risk. At this stage, EDI often emerges as the default choice for large-scale hydrogen projects. What looked futuristic in pre-feasibility becomes the safer, bankable option in feasibility. Specialized RO membrane systems, particularly for seawater, highlight the tension between stages clearly. At pre-feasibility, seawater RO is treated like a black box. Developers assume energy consumption between 3.5 to 5.5 kilowatt-hours per cubic meter and assign a benchmark cost. The key question is, does desalination make the hydrogen too expensive? But feasibility forces deeper answers. Engineers analyze boron rejection rates, design two-pass systems if necessary, and calculate anti-scalant dosing precisely. They choose high-pressure membranes, model intake and outfall infrastructure, and integrate energy recovery devices like Pelton turbines or isobaric chambers. Energy demand is optimized to reduce OPEX, and redundancy is added to minimize downtime. At this stage, seawater RO is no longer a footnote but a critical system that must operate for decades under tough conditions. Ion exchange membranes are another option that shifts meaning depending on the stage. At pre-feasibility, they are rarely chosen unless contaminants like nitrates or fluorides are identified in the feed water. Their complexity and cost often push them aside. But at feasibility, if those contaminants exist, ion exchange membranes can become essential. Electrodialysis reversal stacks are specified, power consumption is modeled, and stack replacement intervals are planned. In some cases, ion exchange membranes are the only way to polish water to meet strict electrolyzer requirements. What was a marginal option at pre-feasibility can become a central feature at feasibility. Distillation, the oldest water purification method, follows a similar arc. At pre-feasibility, it is usually dismissed outright. Too energy-intensive, too costly compared to membranes. Unless a project clearly has access to waste heat, geothermal, cogeneration, or solar thermal, it is not considered. But at feasibility, it can resurface. Engineers calculate thermal balances, design condensers, and model integration with turbines or geothermal wells. If waste heat is abundant, distillation suddenly looks attractive. It can handle heavily contaminated or microbial feed water better than membranes, and its reliability can be unmatched in niche cases. What looked like an outdated option at pre-feasibility can become the best solution at feasibility. The critical point across all these technologies is that pre-feasibility and feasibility are fundamentally different conversations. Pre-feasibility is about assumptions, benchmarks, and screening. Developers are asking, if we add this technology, does the project still make economic sense? The answers are broad and comparative. Feasibility is about engineering, vendor guarantees, and financial risk. Financiers want to know exactly how much energy, how many chemicals, how much maintenance, and how much downtime. A system that looks simple on a spreadsheet at pre-feasibility can turn into $1 million risk at feasibility. The economics reinforce this point. At pre-feasibility, water treatment might be estimated to add 10 or 20 cents per kilogram of hydrogen. At feasibility, when chemical deliveries, resin replacements, and energy consumption are modeled, the real number could be 50 cents or more. In a market where hydrogen economics are already tight, that margin can determine whether a project is bankable or abandoned. This is why investors pay close attention to water treatment during feasibility. It is not glamorous, but it is decisive. From a critical perspective, each technology shifts in perception as you move between stages. RO is always central, but it shifts from assumed baseline to detailed, engineered system. DI looks cheap early, but costly later. EDI looks futuristic early, but reliable later. Ion exchange membranes look irrelevant early, but essential later. Distillation looks outdated early, but valuable later in the right conditions. This evolution highlights how techno-economic analysis is not just about cost, but about risk, scalability, and long-term performance. For developers and consultants, the lesson is clear. Don't underestimate water treatment. At pre-feasibility, it is tempting to treat it as a line item. At feasibility, it becomes a design challenge that can make or break the economics. Understanding how these technologies evolve from assumption to reality is the key to building bankable hydrogen projects. So the next time you hear about a massive hydrogen plant, Remember that behind the headlines is a team of engineers worrying about silica fouling, resin regeneration, and distillation balances. These hidden details are what decide whether the project delivers clean hydrogen at scale or fails to meet its promises. Hydrogen's hidden cost is not just electricity or capital, it is water, and pure water decides project success. If you want to go beyond the headlines and master the decisions behind hydrogen water treatment, electrolyzer operation, and project financing, check out our Green Hydrogen Project Development and Financing course at Renee Energy. Comdories. Inside, you'll find tools, case studies, and templates to help you move from theory to practice. The link is in the description below. Don't just watch the hydrogen revolution. Learn how to build it.